BesselJ function. BesselJ function is a first kind Bessel function with the syntax BesselJ x comma n. X is the value at which to evaluate the function, and n is the order of the Bessel function. In this value, we assign the orders from 0, 1, 2, and 3. So data validation of the list 0, comma, 1, 2, and 3. So we have a Bessel J function to the order 0, 1, 2, and 3. And the formula of the Bessel J function is J sub n, which is the order of x, equals to the summation of k from 0 to infinity, well, value k is 0 to infinity, of negative 1 to the power k, all over k factorial times gamma of n plus k plus 1 times x over 2 to the power n plus 2k. We'll factor out this 1 half, 2.5. So that's why we have 0.5 to the power 2k plus n. And we have negative 1 to the power k in the numerator part, and the denominator will be k factorial times gamma n plus k plus 1. So our values for k will be from 0 to infinity. So we'll try to get to infinity. 0, 1, 14 is good enough for infinity. So we can now use the Taylor Maclaurin series sum. So array formula, series sum of the x values raised to the power starting from n. And the interval will be, that's x to the n and then 2k. So 2, 0, 2, 4, 6, 8. So the interval is 2. So we have an interval of 2. And the coefficients will be this range. So we have here the trend line of the polynomial regression to the 10th degree. So we will continue with the coefficients. So we begin with the array formula for the numerator. 0.5 to the power 2 times k plus n plus n. So that's the first part. Let's say 0. Or we'll stay 1. Next, we continue. The other part of the numerator is, that's times minus 1 to the power k. So we have completed the numerator part. This time we will have the denominator part. So we'll divide this, separate this. That's divided by another denominator will be factorial k times gamma of k plus 1, n plus k plus 1. So n plus k plus 1. We want this to be a separate portion. And we want this to be a separate portion. Okay. Now we have the trend line, which is a decaying sinusoid. So 2 and 0. That's a cosine, decaying cosine. This one is a decaying sine. The 2, also a decaying sine. And 3, a decaying sine function. And we have the coefficients. B0, B1, B2, B3. We'll calculate these values using LINEST. To do that, we will complete the 1 comma x matrix, where we have 0 degree of freedom because the number of rows will be the number of columns. So this is equal to transpose of this value, 0 to 10. And now we can complete the 1 comma x matrix, array formula of the x values raised to the power 0 to 10. Now we can enter the LINEST function. So LINEST of data y and data x. Now we can compare the coefficients from the LINEST generated by LINEST starting with B0. It's negative 9.1 times 10 to the minus 3. That's very small. And we have 1.88 times 10 to the minus 3, which is a match. And negative 6.18 times 10 to the minus 3, also a match. 0.0294 times 10 to the minus 3. 6.62 times 10 to the minus 3, 1.88 times 10 to the minus 3, negative 9.97 times 10 to the minus 4. B7 will be 2.37 times 10 to the minus 4, B8 2.64 times 10 to the minus 5, and B9 1.41 times 10 to the minus 6, and B10 negative 2.96 times 10 to the minus 8. And this is a decaying sine function. We can use 0 to the order of 0. Our B0 matches. B1 also match 0.0123, 132. Our B2 negative 0.28, it's also a match. 0.0442 for B3. So our coefficients match our trend line. Let's see if the regression match to the expansion coefficients. B0 and A1, they match. A0, 0.25, they don't match. Most likely this is the one that matches. This is A2 and B1. And then this is 0.04, so they don't match. We try the second degree, the first degree. 0, our expansion coefficients don't match to our regression coefficients. But our trend line can be generated using the LINEST polynomial regression.